Maurice, a former high ski student, is the COO of the company Peach Inc. Peach Inc. is the leading technology company in Switzerland producing laptops and tablets. Due to the global pandemic, the company faces a supply shortage for materials used in both products. Besides that, the company had to fire employees and are therefore also limited in the amount of labor hours available. Maurice must now decide how he allocates the available resources to maximize profits until the problem of limited labor hours and supply shortages resolve. He remembers learning about the concept of linear programming in his operation management class at the University of St. Gallen. Given the fact that they only have a limited number of resources at their disposal, linear programming helps to leverage them in a meaningful way. Linear programming is one of the simplest methods to perform optimization. By using linear mathematical functions to simplify complex relationships, linear programming finds the most optimal solution to problems with limitations such as budgets, finite materials, a tight amount of labor hours, or restricted machine times. These kinds of problems are also known as constraint optimization problems. Contrary to what the name suggests, linear programming is not about computer software programming. In the language of decision modeling, programming usually refers to setting up and solving a mathematical problem. While the main goal of linear programming is to optimize resource allocation decisions, there are generally two types of optimizations: maximization and minimization. Whereas maximization may involve components such as profits, revenue, or productivity, minimization typically involves categories such as costs or time. In Maurice's case, he must maximize profits with the available resources the company has left. Typically, the goal of linear programming is summarized in an objective function, which is a mathematical expression used to determine the optimal solution to the constraint problem. In the case of Peach Inc., this function is used to determine the production quantity of each product to maximize profits. The production quantities X and Y are the so-called decision variables. The coefficients are the profits each product generates. The constraints are the limited resources Maurice must allocate. Also, a non-negativity constraint exists as Peach Inc. cannot produce a negative number of products. There are four assumptions which define linear programming. The first assumption is linearity. Linearity implies that when scaling production, the relationship between input and output stay the same. The second assumption is certainty and requires that values of the parameters are known and constant. The third assumption is non-negativity, as decision variables cannot have negative values. The fourth and last assumption is that of divisibility, which means that non-integer values of decision variables are acceptable. Maurice's problem can be solved graphically because there are only two decision variables: the production quantity of laptops and the production quantity of tablets. Maurice assigns each variable to an axis: the laptops to the x-axis and the tablets to the y-axis. The constraint function for the labor hours is that 4x plus 6y needs to be lower than or equal to 2000. The inequality sign of the function must be changed to an equality sign, so that Maurice can solve this function for x and y to find the feasible area for the labor hours. The constraint function for the materials is that 4x plus 9y needs to be lower than or equal to 4200. By combining the two coordinate systems, he can find the feasible area because each point in this region will satisfy the linear constraints. He now has two ways to narrow this down to the optimal solution. The first way to find the solution is by determining the intersections of the constraint functions. These intersections are so-called corner points. In Maurice's case, there are three corner points: one at A, one at B, and one at C. To find the corner point that maximizes Peach Inc.'s profits, Maurice substitutes the coordinates of the corner points with the decision variables in the objective function. By doing so, he recognizes that the corner point B has a profit of 42,500 francs, while the corner points A and C both have a lower profit. Maurice now knows that his company needs to produce 150 laptops and 333 tablets to maximize this profit while the supply shortage is not resolved and he has to work with limited resources. Another way for him to find the optimal solution is by using the level lines method. After finding the feasible solution area for both constraints, Maurice must now plot the line that represents the objective function. To do that, he has to set the objective function to z and choose an arbitrary value for it. Maurice decides to choose 30,000 francs for the profit z. To plot the actual objective function, he now solves the function for x and y to find the axis intersections. The x-axis intersection is at 250 and the y-axis intersection is at 286. Maurice is now able to plot a function which is called the level line. He remembers that regardless of the profit z he chooses, the line will be parallel to this one. To maximize Peach Inc.'s profits, he moves the objective function line up. However, he needs to ensure that at least one point on each level line lies within the feasible area. The level line that still touches at least one point of the feasible region is the optimal solution. Here again, Maurice is at point B and the company needs to produce 150 laptops and 333 tablets to generate profits of 42,500 Swiss francs. Maurice can also solve this problem by using the Excel solver. In the first step, he puts the different components of the model in the table. The objective function helps to maximize profits and the given capacity constraints are the secondary condition of the function. Maurice is up to date with his production facilities and knows how much labor and material he needs for each individual product. With this information, Maurice can calculate the capacity utilization by using a built-in Excel function. The calculation is the sum product of the production quantity and the capacity usage. Now everything is set for Maurice to use the Excel solver to calculate the maximized profit. To access the solver, he clicks on Data and then on Solver. He sets the objective to the cell of the objective function value and ticks the Max button to maximize that cell. After that, he puts the decision variable cells as changing variables. Maurice then adds the capacity constraints by stating that the total used labor and material can only be smaller than or equal to the capacity constraints. In the last step, he selects Simplex LP as the solving method before clicking Solve. The Excel solver then shows a new window where Maurice can generate a sensitivity report by marking sensitivity and clicking OK. The program now maximizes the function, updates the decision variables, and generates a sensitivity report. Maurice wants to take a closer look at the sensitivity report. It shows what happens to the optimal solution when modifying the parameters of the decision variables or the constraints. The sensitivity report is broken down into two parts. The first part focuses on the decision variables. The final value cells show the optimal decision variable solution for the production quantity. So optimally, Maurice needs to produce 150 laptops and 233 tablets. In Maurice's case, both values are above 0. The reduced cost part refers only to decision variables that are 0 in the optimal solution. It shows the amount a coefficient, in this case the profit, must change in order to achieve a positive value for the decision variable. The allowable increase and allowable decrease values indicate how much the value of the coefficients may change without changing the value of the decision variables in the optimal solution. The second part of the sensitivity report deals with the constraints. The final value shows the actual used labor hours and materials. The constraints right-hand side shows the available capacities. In this case, the capacity is completely used and there is no slack between both values. Each constraint has a corresponding shadow price. It shows how much the value of the objective function, in Peach Inc.'s case, the profit, would increase if the available capacity constraint would increase by 1. The shadow prices are feasible for the allowed constraints increase and decrease. Maurice proudly presents his results to Julian, the CEO. as he has successfully maximized the profits during such difficult times. He is so thrilled about the whole process that he tells Julian all about the special features of linear programming. He enthuses over how it optimized the firm's decision-making by evaluating various alternatives, showing the optimal allocation of resources, and even is suggestible to condition changes. Julian, also very educated in the area of linear programming, agrees with all the advantages but reminds Maurice that there are always two sides of a coin and that there are some limitations to linear programming. These especially include the assumptions that have to be made and that are hardly ever precise in practice, such as the linear correlation between input and output, the existence of perfect competition, the estimation of relevant values, and the assumptions of a constant flow of returns, which in practice is either increasing or diminishing. Nevertheless, Julian is very happy with the work of Maurice and sends him to a well-earned vacation in the Caribbean.